So let's talk about one of the few things you can do with alkanes, and this is a halogen addition or halogen substitution on one of the carbons. So we're typically going to look at something like Cl2 or Br2 for this type of reaction. And the easiest example of this is methane. So if we have CH4, we can get substitution of one of the hydrogens. So the overall reaction here will be something like CH3Cl plus HCl or CH3Br HBr. Now this is going to operate through a free radical mechanism. So halogenation of any type of alkane, we're usually going to see the lambda up here to indicate the light. The reason we need the light is that it's the first step in the mechanism which dissociates the bromine or chlorine into a radical. So if we have bromine, the first step with the light is to give us bromine radicals. Next step in the mechanism is that our bromine radical is going to attack hydrogen, cleaving this HC bond to give us HBr and the CH3 radical. The CH3 radical further reacts with the bromine radical to give us CH3Br. So this is the general gist of the mechanism. We take our halogen, split it with a source of light to give us a free radical source. Our free radical will abstract the hydrogen first, creating a radical on the carbon. Carbon radical will then attack the other half of the radical to give us the bond. Now, a few comments on this. First of all, the radical is most stable on more substituted carbons. So with Cl2s and Br2s, they're going to typically substitute the more substituted carbons. So for something like CH4, this is going to go slower than something like C2H6, something like ethylene. If we have, for whatever reason, this compound, so we have 1-methylpropane, we'll typically get substitution on the more substituted carbon first, but we can also get subsequent substitutions on other carbons. So the big roadblock with this, or a big issue with this reaction, is that it doesn't stop. So something like CH4, when we do the first substitution, we'll also get a second, a third, and possibly a fourth substitution. So practically the way we control this reaction is we just limit how much chlorine or bromine is inside the reactor. If we make Cl2 and Br2 a limiting reagent, we are more likely to get our mono substitutions than we want. Now the other thing is just be judicious in what we work with. So Br2 here is going to be more selective than Cl2. So if we are going to add a radical to carbon, or we want to functionalize our hydrocarbon, the best way to do this is with Br2. Other big thing about Br2, while it is horribly toxic, it is not nearly as horribly toxic as Cl2. So Cl2 gas will kill you pretty quick. Br2 gas will kill you too, but it tends to be more of a liquid, a little bit easier to work with. But again, the best way to control this reaction, other than working with Br2 over Cl2, is to work with low concentrations of the halogen. This basically limits the likelihood that you're going to see di-tri-substituted halogens when you finish up.